Thank you very much. So hi everyone. For the last talk of the day, I will be presenting our work on a non-observable quantum random oracle model. This is based on joint work with Navid Alamati and Daniel Masny. Since this is the last talk of the day, I will keep things at a very high level. Funnily enough, so the title of my talk can also be abbreviated as, no QROM. We no longer want to use the QROM. We are sick and tired of it. But on a serious note, my talk will be about what can be achieved if we partially use the QROM, like we only use certain features of the QROM and not all features. So before we discuss our no QROM in more detail, let's revisit the classical ROM introduced by Bellare and Rogoway in a cryptographic context. So in this model, hash functions used in crypto systems like PK schemes or digital signatures, they are modeled as random oracles in a formal security analysis. In such an analysis, we also give an adversary classical access to this random oracle because the underlying hash function is generally public. Now, of course, security analysis in this classical ROM is just based on heuristics, right? Because real-world hash functions do not really behave as random oracles with a large entropy. Despite this limitation, ROM has found widespread usage in the community because it allows one to establish security of efficient and practical crypto systems. So now, analysis in this classical ROM, they still further make some further non-standard assumptions. So one assumption is the so-called observability, where we assume that we can observe the queries made by an attacker to a hash function in their attack against the crypto system. And another assumption is the so-called programmability, where we assume that we can somehow modify or program the random oracle, which is somehow undetectable or indistinguishable in the view of an adversary. Now, of course, these assumptions may not make sense in real world when an adversary is interacting with a fixed hash function somehow locally away from everyone in their attack. Hence, there have been quite some works in the literature to eliminate or at least weaken these assumptions in this heuristical security model. So notably, this work by Fishlin et al., they focused on this programmability issue. Specifically, they showed some nice results on which crypto systems can and cannot be shown to be secure when no programming or limited form of programming is allowed. So coming to observability, so this work by Anant and Bhaskar, they proposed a non-observable version of the random oracle model, wherein we are no longer allowed to observe the hash queries or the random oracle queries made by an adversary. Again, in their work, they showed some nice positive and negative results like the previous work of Fishlin et al. So focusing on their positive result, they showed how one can construct a so-called hash-based extractable commitment scheme in their no-ROM. Now, extractable commitment schemes are just your standard commitment schemes with an additional extractability property. So this extractability property is formalized in this following game between a committer and an extractor. So the committer first gets to make some queries to a random oracle. We are using a random oracle because we are interested in hash-based commitment schemes. And since this is the no-ROM, the extractor is not allowed to observe the queries made by a committer to the random oracle. So after this interaction phase, so the committer commits to a message and sends this commitment to the extractor. And the extractor wins the game if it outputs a message which opens to the received commitment. So we say a commitment is extractable if there exists a successful extractor which wins the game for any possible committer. Now, it may seem paradoxical on how an extractor can extract a message because it seems that we are violating the hiding property of a commitment. But as will be seen shortly, the extractor can do so by potentially knowing some trapdoor information. And it turns out that extractable commitments are quite useful in the context of zero-knowledge proofs and beyond. So now it's a nice result that Anant and Bhaskar showed how one can construct an extractable commitment scheme in this no ROM. However, if you want to commit to a message of length m using their specific commitment scheme, the resulting commitment is quite significantly larger than the message, specifically by a multiplicative factor of log lambda, where lambda is a security parameter. So in this presentation, we'll be using asymptotics mainly. And also to evaluate their hash, to evaluate the commitment scheme, they have to run this underlying hash function for each bit of the message. So even the runtime of your commitment is somehow quite inefficient. And this arguably defeats the whole purpose of using heuristical security models in the first place, because we use heuristics to come up with more efficient cryptographic schemes. So it appears that this is the price we have to pay when it comes to the efficiency of our schemes in order to be able to prove security in a more realistic security model which uses weaker heuristics. But in our work, we show that this need not be the case. So specifically, we improve upon the extractable commitment scheme of Anant and Bhaskar, which on the one hand, significantly shorter, as in it is larger than the message only by an additive factor of long lambda and not a multiplicative factor. And it is secure and extractable in their no ROM model. In fact, our commitment scheme is quite simple. So it is essentially this textbook hash-based commitment scheme that maybe some of us have seen in graduate texts on cryptography, where to commit to a message, we hash the message along with some random string. Now, till now in my talk, we haven't discussed anything quantum at all. And this conference is called PQCrypto for a reason. So the quantumness in our work comes from the fact that we go on to show this specific textbook hash-based commitment is secure and extractable in the scenario when we allow the committer to make quantum superposition queries to a random oracle. And of course, without the extractor being able to observe or measure these queries. So before we talk about, also we call this setting the no QROM. And before we discuss the no QROM in more detail, let's again revisit the classical ROM of Bellary and Rogaway, where the adversary only has classical access to the random oracle. And then, relatively like a decade ago, Bonnet et al., they proposed the so-called quantum random oracle model, where now the adversary is allowed to make quantum superposition queries to the random oracle. This is supposed to capture the ability of an adversary in a post-quantum setting to take a public hash function, implement it on a quantum computer, and evaluate this hash function on a superposition of inputs. Now, ever since its introduction, there has been significant progress in the literature on adapting security analysis in this classical ROM to the QROM setting. However, most security proofs in this QROM literature, they rely on this observability assumption. That is, this ability to somehow measure an adversary's random oracle queries. Hence, in our work, we somehow strive to eliminate this observability heuristic in the post-quantum setting by introducing and formalizing the so-called non-observable QROM. And after formalizing the model, we not only construct extractable commitment schemes which are secure in this no QROM, as seen previously, but we also construct important cryptographic primitives such as unforgeable digital signatures and CCA secure PK schemes. So in the rest of my presentation, I'll be going over each of our contributions at a high level. So coming to the modeling aspect on how we formalize this no QROM, so our model is divided into two phases. So the first phase is what we call a setup phase, where the adversary is not yet allowed to make any queries to the random oracle. And in the query phase, where we allow the adversary to make queries. Now, again, remember that we are not allowed to observe or measure the adversary's quantum queries. But in order to have some meaningful security analysis in this model, in order to have like a meaningful reduction, we do allow some form of programming of the random oracle in the setup phase. So specifically, our programming consists of replacing this truly random oracle H with another oracle F, which is indistinguishable in the view of an adversary when it is allowed to make quantum superposition queries to the oracles. And by replacing this oracle H, we potentially receive some trapdoor information that we will be using in the subsequent analysis in the query phase. So we'll be seeing specific examples of this programming when we discuss extractable commitments in the next section. And then in the query phase, we allow the adversary to make queries to this programmed oracle F. Also, we are allowed to interact with the adversary and the programmed oracle over separate channels. But what's important is that we don't observe or measure the adversary's queries to the random oracle. Of course, our interactions can also be over quantum channels, but in our work, just classical interaction sufficed for our purposes. So to conclude this modeling aspect, so note that in our model, we do allow some limited form of programmability, which we call non-adaptive programmability. Non-adaptive because we program the random oracle which does not depend on an adversary's random oracle queries on the fly. So we program before the adversary gets to make any queries in the setup phase. So technically, our model should have been called non-observable, non-adaptive programmable quantum random oracle model, or no-NAP-QROM, but we just decided to call it no-QROM for short. Also comparing our model to the classical no-ROM of Anant and Bhaskar. So in their model, they model this random oracle with a Turing machine which can maintain some kind of a state. So this state will be useful to answer an adversary's random oracle queries. This state can be, for example, a polynomial number of elements, random elements in a list, such that the adversary's first query will be answered with the first element, the second query with the second element, and so on. However, in the quantum setting, this can be a problem, because recall that in the quantum setting, an adversary can make a query which can be a superposition over exponentially many inputs of the oracle. So hence, maintaining such a list or maintaining such a state is inherently incompatible in the quantum setting. And that's why in our work, we rely on a stateless and like a one-shot programming of the random oracle. So now after discussing the modeling aspect, so now I'll be focusing on how we construct extractable commitments in this model. So again, recall that we show that this textbook commitment scheme is secure and extractable in the no-QROM. By secure, I mean it also satisfies the properties of hiding and binding. But I won't be discussing those properties in this talk, but I'll be only focusing on the extractability. So first, in our analysis, we interpret the random oracle H as being the concatenation of two independent random oracles, H prime and H double prime, of certain domain and codomain. As a result, we also allow the adversary access to these internal random oracles, H prime and H double prime. Now, coming to the domain and codomain of these internal random oracles, so for H prime, we require H prime to have the same domain and the same codomain. That is, H prime is a length-preserving hash function. We need this property to show extractability later on. Coming to H double prime, we don't require it to be length-preserving, but we at least require its outputs to be long enough to ensure some kind of binding. But again, I won't be focusing on the binding property. All right, so now let's see how we can show that this commitment scheme is extractable in the no-QROM. So first, in the setup phase, we first assume that the adversary makes at most a certain number of queries, Q queries, to the random oracle H prime. And then we replace this oracle H prime with a uniformly random polynomial of degree 2Q minus 1 over the domain / codomain of H prime when interpreted as a finite field. So the reason this replacement works is because Zandri showed a very nice result. So he essentially showed perfect indistinguishability of the oracles H prime and F with respect to any adversary making Q quantum queries to the oracles. As a result, so then we retain this trapdoor information, which is essentially the description of the polynomial f, because polynomial f is of degree 2q minus 1. So hence, we only need to store 2q coefficients, which is short enough for our purposes. And now let's come to the query phase. So again, we allow the adversary access to these program oracle f and the random oracle h double prime. Afterwards, the adversary sends a commitment to the extractor. So the commitment will be of the form f of message comma r concatenated with h double prime of message comma r. F because recall that we are replacing the oracle h prime with f. Now for simplicity, let's replace the tuple message comma r with just x. And again, further on, let's assume that the first part of the commitment f of x is called y1 and h double prime of x is called y2. So now to win this extractability game, the extractor needs to recover x from this value y1 concatenated with y2. Now recall that f is a polynomial, right? So now this essentially boils down to solving x from y1, where y1 is a polynomial output. So the extractor can do so by computing roots of the polynomial f minus y1. And to compute the roots, the extractor can use any off-the-shelf root finding algorithm over finite fields. Also, it's a basic property of mathematics that if you have a finite field polynomial of a certain degree, let's say d, then you can have at most d roots. So it's possible that when the extractor computes some polynomials, it obtains more than one root, out of which one is the root we want, the small x. So in order to recover the right x, then the extractor uses the second part of the commitment, y2, as a tag. Namely, for each root that the extractor computes, it then interacts with the random oracle h double prime, and then it checks if h double prime of x prime is equal to the tag y2 or not. So once it finds such a root, then it outputs the message contained in it. So it's not hard to see that because of this, the final commitment is perfectly extractable in this no QROM setting. It's also worth pointing out that our extraction strategy of using finite field polynomials in this way in this quantum setting, it's inspired by a similar extraction technique used by Targi and Unruh, where they used it in the context of proving CCA security of Fujisaki-Okamoto transformation in the plane QROM. So if time permits, we'll be discussing this in more detail near the end of my presentation. All right, so I will conclude this section on extractable commitments by noting that in our work, we obtain further shorter extractable commitments where we used an alternative technique of Zandri called small range distributions. But one downside of this commitment is that for perfect extraction, we need relatively inefficient extractors. Also in this talk, we haven't discussed at all about hiding, but in our work, we formally show hiding by first proving that our commitments satisfy a so-called non-malleability property, which in turn implies hiding. Again, details can be found in our paper if you're interested in this sub-area. All right, now let's shift our attention to unforgeable signatures in the no QROM, or formally EUFCMA secure signatures. So in our work, we first focused on a well-known class of hash-based signature schemes called full domain hash signatures, which were analyzed by Bellare and Rogaway which was introduced by Bellare and Rogaway. So on a high level, so such signatures are generally obtained when you take a so-called trapdoor permutation and compose it with a hash function in a particular way. And then to base the security of an FDH signature scheme on the security of the underlying TDP, we use a so-called reduction as shown here. So we first model the hash function as a random oracle, and then starting with any adversary which is successful in forging FDH signatures, we use a reduction adversary which uses the black hat adversary to break the underlying TDP. Of course, the reduction and the signature attacker and the TDP attacker have access to this random oracle. And Bellare and Rogaway, they came up with such a reduction in the classical ROM. Later on, Anant and Bhaskar, they adapted their plain ROM reduction to also prove security of such generic FDH signatures in the weaker heuristical no ROM as well. However, when you go to the quantum setting, so their proof breaks down. So one of the reasons is because so the proof of Anant and Bhaskar, it crucially requires working with a polynomial number of inputs and outputs of the random oracle. However, in the quantum setting, this no longer is the case, because again, a single query by an adversary can potentially be a superposition over exponentially many inputs and outputs of the oracle. Hence, in our work, we overcome this barrier and come up with an alternative security proof for FDH signatures in the weaker no-QROM heuristic. We do so by essentially starting with a security proof of Zandri in the plain QROM setting, and then extend his proof to the non-observable no-QROM setting. However, there's a subtle issue in our result when it comes to real-world applications, because till now there are no known quantum-secure instantiations of TDPs from concrete assumptions like code-based, lattice-based, or isogeny-based. So in other words, we don't have any concrete post-quantum instantiations of generic FDH signatures for which our result could have applied to. Hence, we focused on another broad class of hash-based signature schemes called history-free signatures as introduced by Bonnet et al. So on a very high level, history-free signatures are signatures which have a security proof in the classical ROM via a reduction to a hard problem where so the random oracle programmed by the reduction, it answers the queries of the adversary in a history-free way. That is, the outputs of the of the programmed oracle, they do not depend on past inputs and outputs or past adversarial random oracle queries. And then Bonnet et al. Showed that for such history-free signatures, their classical ROM security proof can be lifted to the plain QROM setting as well. And in our work, we extend their security proof to also prove security in the weaker no QROM setting as well. So in other words, we explicitly identify that only weaker heuristics are sufficient to prove security of such post-quantum signatures. By weaker heuristic, I mean we don't even have to observe the adversary's random oracle queries. And importantly, such history-free signatures do have concrete post-quantum instantiations. For example, they include the so-called lattice-based GPV signatures, Fiat-Shamir signatures, etc. So all in all, we hope that our no-QROM analysis of these post-quantum signatures, which uses weaker heuristics, may find applications in the recent NIST process of standardizing additional signature schemes. Finally, in the last part of my talk, I'll be focusing on our analysis of CCA-secured PK schemes in the no-QROM. So again, starting with the classical ROM. So a standard way to construct CCA-secured PK schemes is to use the so-called Fujisaki-Okamoto transformation, where you start with a CPA-secured PK scheme and combine it with a hash function in a very clever way. And Fujisaki and Okamoto, they proved security of these final PK schemes by using a reduction to the CPA security of the underlying PK scheme. And they did that in the classical ROM setting. So recently, Don et al., they proved post-quantum CCA security of the Fujisaki-Okamoto transform PK schemes in the plain QROM using a bunch of cool techniques. However, these prior security proofs, they crucially rely on these assumptions that I stated earlier on, namely this assumption of observability and programmability. In our work, we come up with an alternative CPA to CCA security transformation for PK schemes in the weaker no-QROM heuristic, where we don't rely on this observability assumption. But a downside of our transformation is that the final CCA secure PK scheme incurs quite some overhead when compared to the starting CPA secure PK scheme. So namely, if you again go back to the original FO transformation, the reason why it is attractive in practice is because it allows one to boost CPA security of a PK scheme to CCA security without sacrificing efficiency. So here I showed the relative ciphertext sizes of the starting PK scheme and the final PK scheme. And as you can see, the ciphertext sizes are roughly similar. However, when it comes to our alternative transformation, there's a huge blow up in the ciphertext size. So hence, I'm not recommending that we use this transformation in practice. And this should be seen as a theoretical result. And probably here is where I reveal reveal my hypocrisy because, as I mentioned earlier on, the reason we use heuristics is to obtain more efficient schemes. So this can be, so an open problem is to obtain more efficient CPA to CCA transformations, where in the security proof you don't rely on observability. So I will sketch our CPA to CCA transformation in the final slides. So we essentially started with construction by Coppola and Waters, where they showed how to construct a CCA secure PKE scheme in the standard model, that is, you don't use any random oracles, where you start with a CPA secure PKE scheme and then use a peculiar primitive called a hinting PRG, or a hinting pseudo-random generator. So I won't be going into details what this hinting PRG actually is, but you can think of it as a standard PRG syntactically, but it offers a stronger security property, stronger than the requirement that the PRG outputs be indistinguishable from random. And a key observation we use in our work is that when you model these hash functions as random oracles in the no QROM, they essentially behave as hinting PRGs. To formally show this behavior, we had to adapt a popular proof technique in the plain QROM known as the so-called one-way to hiding lemma, and we had to adapt that proof technique to the no QROM setting. Again, details can be found in our paper. And so essentially, our transformation is the same as the Coppola and Waters construction, but wherein we replace their hinting PRG with a hash function, and then in the subsequent CCA security analysis, we replace the hash function with a random oracle in the no QROM. So yeah, so that brings me to the end of my talk. Thanks for your attention, and I'm happy to take any questions.
Are there any questions, comments? If not, we are quite exactly on time. There is one question. Here we go.
Thanks for the talk. Do you think it's possible to prove, for example, Fiat-Shamir signature in this non-QROM model?
So yeah, that's a good question. So we didn't directly look at it, but all known proofs involving the FS transform in the QROM, it appears that at some point you have to measure some query when you're doing this extraction. So I mean, it can be seen as an open problem, but at least there's no clear way how you can do it in a non-observable way where you don't measure or observe any queries. So yeah, so to answer your question, we didn't look at it in our work, but yeah, it would be very interesting to see if it can be done or not.
Yeah, thank you.
If there are no further questions and there are no announcements from the local organizers, I think this closes this session. We will reconvene tomorrow at 9 o'clock, and let's thank everyone once more.